Okay. Instead of having a circle, like the last case, we had a circle and it was two-dimensional circle. Now we have a sphere. Okay, good. Sphere is 3 dimensions automatically. Think about a basketball. Now, sphere is one of those shapes that you really need to memorize the formula. You just have to know it. Okay, I'm telling you guys now. And does anybody know what the sphere is?
This,
The volume, sorry, not the surface area. Yes.
isn't it? No. I had it. Like I got it in my mind.
Anybody know the surface area?
No. I know it's nothing cubed though. For space.
It was like 2 pi r plus base times height or
It's like
something
2
like that.
circles
Close.
coned
Two
in.
hemispheres.
That's good, Karen. The way you're thinking about it is right. She's thinking about surface area as like, you know, like a
It was
circle and another
two
circle together. That's how we get the surface area. I don't know if you remember this, but I did it in geometry. And we derived where the surface area comes from. I know. This is like 2 years ago when you guys were like, derive? What does that mean? Now, we use it all the time. But if you remember, if you ever want the surface area of a sphere, it's just 4 circles.
Oh, yeah.
So 4 pi r squared. That's what I want you to remember. If you took a baseball part and you literally took all the coating or all the covering around from it and you cut it up, you're going to get 4 little circles. Okay? So each of those circles. So if you want to memorize the surface area of a sphere, think 4 pi r squared.
That's the surface.
Surface area. Now, the volume is a little bit different. It's 4/3 pi r cubed. Okay? So just little side notes for spheres, and this is before we even start the problem. For spheres in general, you have volume is 4/3 pi r cubed. Again, this has to be memorized, or you know what? Maybe we can find another calculator app to put this in. You can always type this in your own program, by the way, and store it. You go to program and type your own program and type all the notes you want in your calculator. So if you can't memorize this, just type it in. I really don't care. Okay? I don't mean like that. You know what I mean? It doesn't bother me if you use your calculator to help you with that. Because you don't really have to memorize it. I've memorized it because I've used it so much. That's the only reason why. But you don't need to memorize this kind of stuff. Now, air is being pumped into a spherical balloon at a rate of 5 cubic centimeters per minute. Okay? Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. So, let's go back to today. So we started today with dreads. Diagram, related rates, equation, differentiate, substitute. Okay, for some of you, this will be the first problem you're looking at. So again, we're starting with dreads. Can somebody tell me what a diagram would look like of this?
It would be like a circle, be like a curve or something.
Very good, to show the 3rd dimension. So if you're drawing a diagram, so the first part for diagram, draw it like this to show the 3rd dimension, to show that it's a sphere. Okay? Always, whenever you draw a sphere, draw a circle and then an ellipse. That's an ellipse inside. Now, with this circle, you want to label everything you know. What are the only things about a circle or sphere that you really know?
Radius.
Diameter or radius, either one. Now in this problem, they use the radius change and then the diameter. Personally, on the SAT, I think they're always going to use radius. They traditionally don't use diameter in math. Radius is usually used. So I would recommend using the radius rate. If you're given all of your info in terms of a diameter, then use a diameter. But you're given both the rate of the radius change and you're given the diameter's length. So instead of giving the diameter's length, you can convert that to radius in a minute. But that's our diagram. That's all we know. This thing? This? D for dreads. So we did diagrams so far. Now we're on R for related rates. Yes?
If the volume divided volume.
This is what we're going to use, but these are things that I talked about in the beginning, saying that you really should have them memorized for a sphere. This is the surface area.
Justice,
It's 4 circles.
Jamal
See how that's a circle right there? Pi r squared. There are 4 of them on the outside. For volume, you just have to memorize.
Shante Crawford.
So R is related rates. Anybody remember from today? What did that mean, though?
Related rates, that's not.
What did that mean? That was the tough
What
one.
changes over?
We're trying to figure out what is changing. So in this problem, what is changing? Determine the rate at which the radius of the balloon is increasing. So the radius is what? Changing. It's increasing. So we are finding dr dt. Again, now we're on, remember, we are on related rates, the second part. So we're trying to figure out what is changing. The radius is changing. How is it changing over time? So there's your time, dr dt. That's the first thing we want to look at. Now, what are we given that is changing? What are we given?
The rate, diameter,
Joshua.
You're given the diameter at a certain point in time, but the diameter is not necessarily changing. They're telling you the diameter is 20. So we could write,
Report to my office at this time.
we could write that down as a little fact, okay? What's changing? The volume. At what rate is it changing, Christian?
5 centimeters
Per?
per minute.
Very good. So again, look, air is being pumped into a spherical balloon at this rate. How did you know it was volume? I don't see the word volume on here anywhere.
You too?
Because it's cubed. Take a look. Look at the units. Remember the units I keep talking about? If you look at the units, you're going to see centimeters cubed per minute. When you see centimeters cubed, it means that it is changing in volume. If it was centimeters squared, what would it be changing? Area. If it was just centimeters. Length. Very good. So again, this is the volume changing rate. So we start by saying dV dt, the volume is changing at a rate of 5 centimeters cubed per minute. We know this, we are trying to find this. Again, if you follow this process every time, you cannot do poorly in this topic. You have to start with your diagram. We did that. We labeled it. We then went to related rates. Just list whatever is a related rate. We are trying to find at what rate does the radius change, the rate at which the radius changes with respect to time. We're solving for this. That's what we're going for. What do we know? We know the rate at which the volume is changing. They're going to play a role in one another soon. We also happen to know what the diameter is. Okay, if we know the diameter, what do we also really know? Which is what? Thank you. So please list it. Okay, again. So again, we know that the radius is half our diameter, so we don't even need it anymore. Okay, we don't need the diameter anymore. And again, you want to go to one or the other. You don't want to use diameter in one part of the problem and radius in the other. Okay, this was just given to you this way so that you can recognize the fact that if you're given a diameter, you might have to change it. So, that's D and R. What does E stand for again? Equations. Now, Rosie, you said equations, so I'm going to follow up with your answer here. If we are looking at this problem, look at what, please don't answer other people. Look at what we're given here. Are we going to use volume or surface area? How come?
I think because of the cube.
Very good. That's absolutely right. You know the volumetric, this is called the volumetric flow rate, or the cube part, where it says volume. If you know the volume part, you know you're going to be using volume as your formula. You're not going to be using the surface area formula for a sphere. Again, because you know dV dt, you know the volume changes at a rate of 5. Okay, because of that, you're going to be using volume. So when we identify our equation, we're going to use volume. Now, this was the tricky part from today coming up now. When we take the derivative, which is the next part, differentiate. Differentiate. How did we take the derivative? What method did we use again? Implicit. Very good, John. Thank you. Implicit. We use implicit differentiation today because we are not given like f of x here. We're not giving g of x. We can't just take the normal derivative. We need to think back to think when we had derivatives, when we had implicit. So the example that if you look at the top of the board, the whiteboard over here, when we did implicit, whenever we took a derivative of y, we put the dy dx. Whenever we took a derivative of y, we put the dy dx. For this kind of a problem, whenever you take a derivative of anything, because nothing has a t in it, notice there's no t's anywhere. Whenever you take the derivative, you put it over dt. So again, if I continue this problem, what is the derivative of v by itself? Just 1. Again, think of the derivative of like x. The derivative of x would just be 1. Think of this as x. So it would just become a 1. But then we write dv dt next to it. Again, every time you take a derivative with related rates, you always put d something dt. And the something comes from whatever you took the derivative of. So since we took the derivative of a v here, it became dv dt. When I take the derivative over here, what am I going to tack on? dr dt. Okay, whatever you take the derivative of. Here, taking the derivative of this, put the 3 on front.
4, 5,
4.
4,
Squared.
Carrie? Not circumference, but be careful. Other word? What's the word? Surface area. Notice. Remember today, when we took the derivative of the area of the circle, we ended up getting the circumference? We had the 2 pi r. Remember today we took the derivative of the area, we got 2 pi r, it had circumference. When you take the derivative of volume, you're going to get the surface area. It always works that way. Because when you take a derivative of something, you're lowering the dimension by 1, really. Okay? You're going from cube to square. Now, here, at this point in time, we want to look and say, okay, I've got all this information now. I've got the equation, that was E, sorry. I differentiated, which was D. That was the last part. And then what's the last thing say to do? Substitute. Well, take a look. What are we trying to find, people? Very good, Carrie. It's in the box here. We are trying to find dr/dt because this problem said, determine the rate at which the radius is increasing. Determine the rate at which it's increasing. So the rate at which r is changing. So you're finding dr/dt. Now, with that said, just plug in. You know everything. You know dv/dt is 5. Plug in the 5 over here. You know what the radius is. What was the radius, guys? 10. It was given as 10 here. So plug in the 10 for the radius. I'm sorry, I need units. I apologize. Please yell at me if I don't put units. Not yell, but it can kind of be nice. The radius was 10. Now, dr/dt, it looks fancy. It's like a variable, guys. Just solve for it, okay? Just solve for it. So, divide by 4 pi, divide by 10 squared, and solve for dr/dt. Let's go through that process.
Those two things more like plugging in.
Yeah. I couldn't put a P
Yeah,
at the
yeah,
end,
of course.
so it would be dripped. I don't know.
Why does it find
Okay, I just put this as 100, people. 10 squared is 100. Okay, divide by the 4 pi 10. Just get rid of everything next to dr/dt. So divide both sides by this quantity right here. And take a look. First of all, you're going to see some cancellation of units. You have centimeters cubed and centimeters squared. So these squared cancel with 2 of those. What are you left with? Look at your units now. Centimeters per. And we're looking at the rate at which the radius is changing. The radius is a length. It's a length. So it's got to be centimeters per minute. It can't be centimeters squared per minute. We're not looking at the area change anymore. So at this point in time, just divide through and you get dr/dt. If we solve this, what do we get as an actual number? No, I didn't get the answer. I just left it as 1 over 80 pi, yeah. Okay.
like 5?
So if you cancel these two, make that a 20, make that a 1, right? 5 over 100 is 1 over 20, really. Reduce, common fractions. 4 times that is 80 pi. And yes, it's going to be a very, very small number. Let's think about this now, logically. You have a balloon that has a radius of 10 centimeters. So it's got a diameter of 20 centimeters. 20 centimeters is about this big. Don't think about 20 inches. 20 centimeters is about 2/3 of a foot. Okay, a ruler. Actually, I have a ruler right here. So, what we have going on right now is so to scale, I'm going to draw this on the board now. We have a 20 centimeter diameter of a balloon. It always does this when I put these up on the board. Okay, it's not a straight line. That's 20 centimeters. That's all it is. So imagine if you had a balloon with a diameter of that big. So this is the diameter in both directions. So it'd be about that big. So we're looking at a balloon that's about that big. Okay? Now, if you're putting into the balloon 5 cubic centimeters per minute. Okay? A cubic centimeter is simply this. A centimeter by a centimeter by a centimeter. So we're looking at literally a cube this big. If you're literally adding this much air into this shape. Remember, this is a sphere. You're adding this much air into that shape every minute. Is that a lot of air? No. Think about when you blow up a balloon. You probably add in, and again, sorry, it's 5 of these. 5 of these. Because it's 5 centimeters, right? It was 5 centimeters squared per minute, right? Cube per minute. So you're adding 5 of these little cubes in there every minute. You can add 5 of those cubes in with one breath. Think about it. Blow up a balloon. You can easily blow 5 of these into the balloon. That much quantity of air. Now, if we think about it this way, every minute you're only adding 5. So the radius is probably not going up by much. And as Carrie said a minute ago, this is a very small decimal. 80 times pi, we're looking at a number like 240. 1 over 240. Okay, a very small decimal, which is logical. It's very logical. Because think about it in your mind. Try this stuff out when you solve these problems. You can do them very easily. Some of the problems are like you know, you have a cylinder that's releasing water at this rate, at this height, you can test them all out. And you can actually set them up. And what I want to do later this week is actually bring one in to show you. But then at the end of the year, we'll do a lot more projects with it. But again, I want you to see that you can actually do this stuff. You can see that it makes sense as your answer. So again, that's our final answer. 1/80 pi centimeters per minute. Who can explain to the class again why it's centimeters per minute as units? Why is the units for this answer centimeters per minute?
Because fractions and units are together.
Okay, they give us centimeters cubed per minute for a volumetric flow
But
rate.
radius is enough.
Very good, that's the answer. So all you need to do is this. Look at your answer, guys. dr. R is radius, right? Radius is measured in centimeters. What is time measured in this case? Minutes. So the answer that you have must match the choices of your units. Okay, so again, if you have like centimeters cubed here, it's clearly not right because that's a volume, whereas this says R. R is a length. T is a time. So if you don't have minutes here, if you had something like, I don't know, inches or something weird, I don't know where you got it from, but say you had something else, it doesn't make sense, okay? It doesn't make sense. These have to match up with each other.
So, if you write the right answer, and you put the wrong, what you put?
On the AP, and this is what I went over for those who were not here earlier.
Yeah.
If you have the wrong units in the AP exam, you don't get any credit.
No credit.
No. You get credit for like the first, remember I talked about the first statement?
Yeah.
So you would probably get credit for like your setup and stuff and all this, but that last point, that's worth 1 point. The last point of the problem, all the setup is up until, the setup is until here. The equation and then the differentiation. From here down is pretty much all worth 1 point, doing all the math and solving. If you do all the right work and have the wrong units, you don't get that point. You don't even get a half a point. Okay, so you might get the points up until here, you might get 1 or 2 points here, but that third point, or I don't know however many points it's worth, you won't get any of them for the units. You have to have the right units. And that goes for velocity and acceleration also. We talked about that today, so if you weren't here, make sure you check out that video from today. Substitute was what we did. Sorry, I didn't label that here. But substitute was plugging in, as Christian said. We just can't call it P, we called it S. So substitute would be from here down. We substituted in the 5, we substituted in the 10, and then we solved. Okay? So you can even put substitute / solve if you want to, as the last line, because you're solving, obviously. All right, let's look at another one. Now, yes? Yes, sorry. The first 2 problems we did, the first one was with geometry and a circle changing. The second one had to do with volume flow rate. So those are 2 of the major topics. Here's one of the third topics. Now I'm trying to give you an example of each. I have a lot of examples to show you, but I want to go through an example of each. Here the problem has to do with particles. Remember I said particles moving away from each other? If we go back to the original, I think it was movement of particles. So what we're going to look at now, we're going to analyze is the movement of a ladder. Okay? And it does help if you're in physics, because we're going to use the word velocity, but if you're not, it doesn't matter. Velocity is just the rate of change. Remember, velocity is the rate of change of position. That's all it is. But I'm going to use that word. A 15-foot ladder is resting against a wall. The bottom is initially, at start, initially 10 feet away from the wall, and is being pushed towards the wall at a rate of 1/4 feet per second. Okay? Again, it's being moved closer to the wall at that rate. How fast is the top of the ladder moving up the wall 12 seconds after we start pushing? 12 seconds after we start pushing. Okay? It's a tough problem. It's not an easy problem here. Now, what kind of a diagram can I start with? What would it be? Good. And what kind of a triangle? A right one. Because again, think about a wall and think about a ladder. There's your ladder right there. So that's my diagram. That's part D. Now, what I recommend you guys do is the following. Always call whatever your base is X and call whatever your height is Y. Okay, call your base X and call your height Y. It will help you a lot to see what you're doing here. Now, that's my diagram pretty much. I don't know what this value is right here. I mean, I know what its value is. It's going to be, using Pythagorean theorem, I know that's what the answer will be. Okay? Oh, thank you. Never mind. It's given in this problem. Even easier. But you know what? Make believe it wasn't given for a second. I want to make sure this makes sense because you're going to have to do this in other problems. This problem's a little easier. Sorry. Here. Where does that come from? Good. Pythagorean theorem. A squared plus b squared equals c squared. Take the square root of both sides. That's what you'll get if you solve for c. But as Houston said, thank you, Houston, for reminding me, there is 15-foot ladder. Okay. So we know that it's a 15-foot ladder. We are trying to figure out again, how fast is the top of the ladder moving up the wall 12 seconds after we start pushing. 12 seconds after. So, what are we looking for? That's our next thing, our related rates. Here's our diagram. Then we have to get to our related rates. What are we looking for? Good. In what? What were you going to say? Yep. So what does that mean, though?
Yeah.
Okay, but let's a little more specifically, Jasmine. How fast is the top of the ladder moving? So if something is moving, what do we call it? It's what?
Height.
Speeding or accelerating. So we're looking for its, what's the term? Velocity. Again, what we're trying to figure out is this. If you want to know how fast something is moving, you're always looking for velocity. Velocity. What is velocity again? Which derivative? First. Acceleration is second.
The original and then the super.
Okay? Sorry. There's your list. Oh wait, XVA. So velocity is the first derivative. So we're trying to find at what rate is this changing up and down the wall? Well, what variable is the vertical variable here? What is this variable? So we're trying to search for dy dt. Adios, amigo. Watch the rest, please, okay? So we are searching for dy dt. Again, we are trying to find the rate at which the ladder moves up the wall. Up the wall is the y direction. This is the x direction. Next, we are given something. We are given some number along the way. That has to do with the rate. Does anybody else see where it is? How come you know that's a rate right away? Good. Right away, Rakab said, you know what? Look at my units here. Feet per second. That must be a rate. Now, what does that tell us? The bottom is initially 10 feet away and is being pushed towards the wall at the rate of. So it's being pushed toward the wall. So the bottom of this is being pushed toward the wall and the top of this is moving up. So again, imagine a ladder. I'm holding a ladder here, okay? If I start pushing the bottom in toward the wall, what happens to this? Does it slide up the wall? So this is moving up, whereas this is moving in toward the wall. So we're moving toward the wall in this direction, but the ladder is moving up. If the ladder was here, it would look like this, right? If the ladder was even closer, it would go even higher up the wall. So we're trying to find the rate at which it changes, but we're given something along the bottom. We're told that it moves toward the wall at a rate of 1/4 feet per second. What can I write? So what can I write from that? Okay, velocity of the x, which is velocity in the x direction.
No, the velocity in the y direction.
We're trying to find the velocity in the y direction.
Oh, so yeah.
It says, find the rate at which it moves up the wall.
So dx equals
Dx dt. Okay, that's what we're given. Again, we are given the rate at which this thing goes toward the wall. Look at your variable here. If this variable is moving, then you have dt there. So you take whatever it is, the x, put it there, and put dt. Since this variable was moving up the wall, we use dy dt. Again, we're trying to figure out the rate at which it moves up the wall. This is what we're trying to figure out right here. This is what we have. What else do we have in this problem? Say again?
We know how fast it's moving.
Okay, we know how fast it's moving. We think about it that way. That's fine. We know that initially it's 10 feet away. We want to know 12 seconds after. The initial what here? Okay, the initial 10 feet away. So we could say, if we wanted to, now there's no room for givens right now, but if I want to list this, I would call this xi equals 10 feet, meaning the initial position is 10 feet from the base. Xi, x meaning the position along this way, is initially 10 feet away. We are also told that the time we're looking for is 12. Okay, but again, that doesn't fall into any category just yet. Do we have any other rate at all? No. The only rate that you ever might have is the change of the rate of the hypotenuse. But since it's a ladder, it's always going to be 15 feet. This is not going to change at all. Sometimes that will change, but it's not in this problem. We'll look at an example where it does change in a minute.
So, if you were to graph this, is the x, like, does it represent time or does it represent like, just the distance?
There's no time here. Time is implicitly, it's like, did you guys learn about, what are they called? It starts with a P. It's types of parametric functions last year?
No.
And I was in pre-calc now? Okay. X is a function of t. It means x changes with respect to time. That's where this comes into play. And y is a function of t, but there's no t displayed on the graph here. It's going to come into play a little bit later. Okay? All right, so we have dr. Next is e. Now, look at your diagram. What's the only equation you can write from this diagram? What is it? Pythagorean theorem. A lot of the time, when you have a triangle and you have two variables that you're missing here, and you're going to have to differentiate them both, you're going to probably use the Pythagorean theorem. Okay, so get used to using it here. So we're going to have x squared plus y squared equals 15 squared. Now, it looks for a second like, all right, you know, it's getting pretty easy. It's not that hard. What's the next step after equation? Differentiate. Okay. So if I take the derivative, now be careful. We're still taking the derivative with respect to time. So we always have to put on the dt at the end of that thing. So what's the derivative of x squared?
2x dx dy.
Dx dt. Remember, this is where it's always dt. Remember, whenever you take the derivative of anything from this point on, whatever you take the derivative of goes on the top, and dt will always go on the bottom. Even when you're plus 2y dy dt equals 0. Why do I have a 0 there? Good, a constant. It doesn't matter that it's 15 squared. 15 squared is 225. The derivative of 225 is 0. Either way, it's still 0. Now, looking at this problem, clearly we can see that we have issues, right? We can't get all of our answers. Let's take a look and see where our issues come about. First, we want to know when the time is 12 seconds. So we have to consider that right away, when time is 12 seconds. Next, we have to figure out, well, okay, what is the value of y? What is the value of x? What is dx dt? We're looking for dy dt. Remember, this is what our goal is. We know dx dt, that's given right here. So I could always immediately place that in there. But I don't know what x and y are. And how do I incorporate this time?
Probably use self-start and self-fill.
Okay, fair enough. Let's continue this process, though, before we go any further. Let's plug in 2x. Dx dt is 1/4 feet per second plus 2y dy dt equals 0. So again, I'm looking for dy dt, so I don't have to worry about that. But as Christian said again a minute ago, we might have to do some substituting in. We need to know what y and x are. We don't know what they are. Okay, we don't know what they are. Now, here is the trick to this problem. This is where Algebra 2 and physics come together here. You know initially how far is x from the base? 10 initially, right? It's 10 feet from the base. We also know that the rate at which it's changing is 1/4 of a foot every second. Am I correct?
Yeah.
Second. And the problem wants to know after 12 seconds. So we can find x at 12 seconds. And let's go through this. Remember, for all things, velocity equals distance over time. Velocity equals distance. Distance is x over time. We know the time. What is the time, everybody? 12 seconds. So I'm going to move the time up over here so that I can figure out what x is and simply plug it in there. Again, I know that velocity equals distance over time. You were given the time for some crazy reason. Well, you were given the time so you could figure out the position of it. Okay, currently, in the beginning, it was 10 feet away. It was 10 feet away. But now we want to figure out where it's gone to. So, what was the velocity? What was the velocity in the x direction? 1/4 what? Feet per second. Okay, so the velocity is 1/4 feet per second. What is the time, everybody? 12 seconds. So how many feet have gone by? 3 feet. Now, what does that mean, though? It does not mean that x is 3. Be careful. Where did it start at? And where is it now going to be then? Where is it going to be? 7. It's getting closer. It said it was moving toward the. Look at the problem. It started 10 feet away initially. The initial starting distance was 10 feet from the wall. And it says that the bottom is initially 10 feet away and is being pushed towards the wall. So now we're at this point here. How many feet did we just lose? What did we say? 3 feet. So where is the position again? 7. Again, we lost 3 feet because we were moving a quarter of a foot every second toward the wall for a duration of 12 seconds, which means 3 feet when you cancel. 12 over 4 is 3. So the x position, or the delta x, really, delta x, the change in x, has been 3 feet in. So now x is 7. So I can go back to my equation now and plug in a 7 here. Okay, that's great. But now I know this. I don't know why still. Plug it in where? You're on the right track. In where? Very good. Into the Pythagorean theorem. Take a look. No matter what, guys, no matter what, the Pythagorean theorem always holds true. So take a look at this statement right here. We know what x is now, don't we? What did x turn out to be? We just said 7. Plug in the 7. Figure out what y is here. And then plug that back into the answer down there. Plugging in, we're going to get root 176, which is about 13. So again, we know that at the point in time after 12 seconds. So let me make it more clear. You see the red triangle? That's the triangle in the beginning. You see the blue now? If I continue like this, the blue is after 12 seconds. That's what's going on here. So initially, the ladder looked like the red one. After 12 seconds, it looks like the blue one.
If you lost the jacket after choir practice, it is in the main
We know
office.
that x is 7. Take that 7, plug it in right there into your Pythagorean theorem. Figure out the value for y so that you can plug in the y right here and then find dy dt. The whole goal is to find dy dt. That was the beginning. We started the problem off by saying, what is dy dt? So in order to find dy dt down on the bottom, we need y. To find y, we need x. To find x, we needed the velocity. So you're constantly using all the information. So if you solve this for y, you're going to get 49 plus y squared equals 225. So y equals the square root of 176. As a number, I don't even know what that turns out to be. I'm just going to leave it like that. It's around 13, okay? Because 13 squared is 169, maybe 13.2. So here, we're looking at okay? Now, what did I forget? Who can tell me?
Your units.
What units am I forgetting here?
I
Explain it.
didn't need to see it. Oh, your y units.
Oh, here?
No, your units for feet. For what?
What are the units of them? Feet for both, okay? So make sure you put a feet in here, and you put a feet in here. Oops, not there, but in here. Okay, again, x and y are feet. They're the distance from the wall, the distance up the wall. All right, let's solve. You're going to get feet squared per second over here. 2 times 7 is 14. 14 over 4 reduces to 7 over 2. So 3.5 feet squared per second. That's what that turns out to be. Here, leave it as 2 radical 176. And again, the feet are going to be applied here eventually. Let's leave them for now. So we got feet still. dy dt equals 0. Sorry, I'm going at an angle there. I don't know what happened. So, if we want to solve for dy dt, move over the 3.5.
Negative.
Okay, again, move the 3.5 over, and then figure out here what you're going to do. How do you get rid of that? Divide. Now, there's one key along the way that's going to come up, and it doesn't matter which way you do these problems, but there's one thing you need to notice. What kind of an answer are you going to get if you do it the way we're doing it right now? What is it, Christian? A negative. Because again, you're going to subtract 3.5, then you're going to divide by that 2 over 2 radical 176. So you're going to get a negative. But dy dt, what does dy dt represent again?
Changing height.
The change in height. Which way is the ladder moving, up or down the wall? I heard both. Up. It is up. I don't know, I heard down somewhere. But the ladder is like this. We're moving the ladder in, so it's moving up the wall like this. So how is it changing? It's changing in the positive direction. So our answer should be positive. The mistake, if you want to look at it, or if you want to call it a mistake, you don't have to worry. You can change it at the end. Would just be this. Why should that be a negative, really?
Because.
What's happening to x? It's getting
Small.
smaller. So if you want to account for the negative there, you can, or you can realize at the end when you get dy dt, it's got to be positive because you're moving up the wall. So use your logic to answer these questions. So subtracting 3.5, we get 2 radical 176 dy dt equals negative 3.5 feet per second squared. Dividing by 2 radical 176, feet, we get dy dt equals negative 3.5 feet per second squared. Is it feet? No, feet squared per second. I'm so used to physics. Feet squared per second. Feet squared per second. All over 2 radical 176 feet. Now, what's going to happen to one of your feet? I know it sounds not grammatically correct. They're going to cancel, right? One of your foot. So this feet will cancel with this. What are you left with as units now? Feet per second, which is exactly right, because y is measured in feet, t is measured in seconds. Okay, and again, you need a positive. You can leave it like that, yes. But I would make my final answer like that. Okay? I would show the units as one entity and make it a positive, because we know we're moving up the wall. Again, you could have taken into account for that with the negative in the beginning there. It doesn't matter. Either way works. I know this is tough. I know it's not an easy topic, okay? We got to go through these kinds of problems. These are the problems that are going to help you learn a lot more than any other topic. Okay, it's all about problem solving, and it's tough to look at these problems and know what to do. Let's check out example 4, which is actually a lot easier. And it looks complicated, but it's not that difficult. Can somebody read besides me?
The base and height of the rectangle B and H, and they are changing at rates P, Q, respectively. Prove the area A is changing at the rate PQ plus HP.
Yep. Okay. The base and height of a rectangle, R, it should say, R, I don't know where that went. The base and the height of a rectangle are B and H, and they are changing at rates PQ, respectively. What does that mean, first of all? If you don't know what that means, you can't even do this problem. Respectively.
They're just saying that.
Not at the same time.
Well,
If I said to you, Jocelyn and Christian, the scores on your tests were a 90 and an 80, respectively. Who got the 90, who got the 80? Why? Exactly. It goes to order. Respectively means look at the order. So, I didn't hear you. So the rate at which the base is changing corresponds to P. The rate at which the height is changing corresponds to Q. Okay? Again, the base and height of a rectangle are B and H, and they are changing at rates P and Q. So dB, dt, and dH, dt are represented by P and Q. Prove that the area is changing at the rate BQ plus HP. All right, well, what do we do? Start with a diagram. We have a what? Okay, we're done. Second, rates. Rates. Carrie. I want to know, Carrie, what dB dt equals from the given information in the problem. At what rate is the base changing? What is it given as? What would it be? Okay, it's one or the other. It's not both. There's a comma there, sorry. So the rate at which they're changing, the base corresponds to the first one, and the height corresponds to the second one. That's what that word respectively means. That's the hard part there. So the rate at which the base is changing is defined as P, and the rate at which the height is changing is Q. Okay? Are we actually trying to find any rates in this problem?
no.
What are we doing? We're proving, right? So we don't have to do anything more with rates. Next, equations. What is the problem asking us about? The what? What is it? Area. What's the area of a rectangle? Now, differentiate. Be careful. Try this on your own. And I'm telling you, there's a little trick, so don't overlook it. Remember, you have to differentiate implicitly here. Nothing is T on there, so you have to use your DD and D whatever after everything you do.
What about the A? The A don't use DADT?
A goes to DADT, yeah. The left side is the easy part. That's DADT, sure. Because there's really a 1 there. You need to take the derivative of the right side. And don't fall into the trap, please. Don't fall into the trap.
I think I got it. I think I did it right. Did get it. Yeah. I'm just gonna follow.
How would you
the shot.
differentiate something that says B times H? What kind of a rule would you use?
Oh my.
Product rule. Product rule. That's where the trick is, okay?
So it's. Oh, that's no.
So, remember, the rule is A times derivative of B plus B times derivative of A.
Oh,
So, start with A times the derivative of B
Can we just put it? Yeah.
plus B times the derivative of A.
Yeah, that's how it goes.
Okay? Again, A times the derivative of B, well, the derivative of H is just 1 dH dt, plus B, which is really H, I know that sounds weird, H times the derivative of A, dB dt. Well, these are given, aren't they?
Yeah.
Plug them in, we're done.
That's right.
That's it. We're just showing to prove. So dA dt equals BH. Now remember, we're taking in these values and we're going to substitute. We differentiate it, and now we're on the last step of substitution. P goes in for the one with the B. So a P goes in over here, and a Q goes in over here. And that's what the answer problem. That's what the problem asks us to do.
So what time is it?
4:50.
My bad.
So what, we got like 40 minutes?
We're doing one more.
10 minutes, 25.
How much we trying to get out?
Yes, I know. We're doing one more, guys. We'll save the hard one for tomorrow.
No.
All right, let's do the easier one. I was going to jump to number 6, but let's just do number 5 for now. All right, this problem, you're given a diagram, and sometimes they will do this, especially when you have an angle. They'll give you a diagram.
Is the D
Because it's
taken
hard to
care of?
designate it.
The D is taken care of.
Yes, the diagram is taken care of. I'm sorry, like D? Yes. The diagram from Dreads is taken care of. 2 people are 50 feet apart. That person is standing still. This person is moving. One of them, again, so this person starts here. They're 50 feet apart. That's where the 50 comes into play. And one person is moving. One of them walks north. So they show you the person is walking north. What would you call that?
Why?
Why? So the rate at which they walk would be called what?
D, Y, D, T.
dy dt. Very good. So no, at a rate, so that the angle shown in the diagram is changing at a constant rate. So they're going to give us an angular change. But again, call this y, please. Okay, in this diagram, they call that x. So don't worry about it. Don't call this x anymore. This is a number. It's 50. Okay, it's not changing. This is not going to change ever. It's always going to be 50. Even if this person moves up to here, the person is still now like 10 feet behind and 50 feet over. They're still going to be 50 feet apart in that direction every time. So you don't have to worry about that. All right. So we know that one of them starts walking north at a rate so that the angle shown, theta, in the diagram below is changing at a constant rate of 0.01 radians per minute. 0.01 radians per minute. At what rate is the distance between the people? What is the distance between the people considered to be? It initially is 50, but after a certain amount of time, what do we call this distance? X. Remember, this is 50 here. In some textbooks, they call it S for the hypotenuse. They're calling it X here because you didn't use an X. But if you used an X and used a Y, you would call this S or D. It doesn't matter. But anyway, what is the distance, the rate at which the distance is changing? So here's the distance of 50. Then that might be a distance of like 55, then 60, then 65, then 70. If I keep finding the hypotenuse or hypoteni, I want to find at what rate are they changing. Okay? When the two people changing when theta is a half a radian. All right. The problem makes it difficult because it's theta now, and people get confused. It is no more difficult than what we've done. Start with dreads. We got the D done already. We're done with that. What you got for R? This is where it's tough.
Do you, what's called DY with DT?
Okay?
Equals.
Do we know that though?
No.
It tells us that the person is walking north at a rate. It doesn't tell us what the rate is. And we're not asked to find that. So we really don't even need dy dt here. Okay, it's a good point to notice, but we don't really need dy dt in this problem right now.
So we need theta.
We might need it eventually, but we don't need it right now, and it's not even given in the problem.
Do we need the theta over d?
Very good. What do we need? D theta dt. Because it says the angle is changing, isn't it?
Yeah.
What is the rate at which it's changing?
Oh. 0.01.
What, in the units?
Oh, RAD is ran by that. I know RAD is
Can you use words?
rad.
What does rad stand for? Radians, thank you. Radians per minute, okay? So again, take a look at what you know. The angle, it says the angle is changing at a constant rate. The angle shown in the diagram is changing at a constant rate. That's where that comes from. Next, we know that value so far. What are we looking for? What are we looking for? dx over dt. We want to know at what rate is the distance between the people changing. The distance between the people is given as x. This is the distance between them at any given point in time. When the person's up here, it would be x like that. When the person is here, that's x. When the person's up here, that's x. X is changing. The problem says, find the rate at which it's changing. So find dx dt. Karen. We, yes, because one person, it says that they're 50 meters apart. In the diagram you can, yes, from this diagram. Yes, absolutely. You hear what the question was or no? Can you assume there's a right angle there? It's not drawn. It should be drawn. If they're going to give you a diagram, it should be drawn like that. Or the problem would say this. Two people are 50 feet apart horizontally, which tells you that this is a flat line. And then if a person walks north, a flat line in north, what kind of an angle do they make?
Right.
A right angle. It didn't say that though, so Karen makes a very good point there. Okay, there should be a label there. It does not say that. Now, we are given one other piece of information. Let's just list it somewhere. We're told that the theta value is 0.5 rad. Okay, we're told that. That's a given. We're going to probably use that somewhere. Now, continuing this problem, I could start with Pythagorean theorem here. There's no problem. I could start with it. And you know what I'm going to do? I'm going to show you real quick that if you start with Pythagorean theorem for your equation, it won't work. Watch what happens. It won't. You don't have to write this. We have 50 squared plus y squared equals x squared. 50 squared plus y squared equals x squared. But when you take the derivative, you're going to have a dy dt here, right? You're going to have a dx dt. You're trying to figure out dx dt. But do you know dy dt?
No.
And it's not given anywhere in the problem. So you know what? Let's not use this one. Let's use SOHCAHTOA. Why am I using SOHCAHTOA? Who can tell me?
Because you need an angle.
Very good. When you're given an angle, think about SOHCAHTOA, please. So here, just write a relationship. Ignore the y. The y doesn't even matter anymore. We don't care about it. If I have the adjacent and the hypotenuse and the angle, what am I looking at?
Adjacent hypotenuse. Angle. Adjacent hypotenuse.
SOHCAHTOA. C-A-H. Very good. So the cosine is adjacent and hypotenuse. So, start with your equation as cosine theta equals 50 over x. The author for this problem that wrote this one also used secant. And he did secant of theta equals x over 50. The reason the author did that was because it's easier to take the derivative here, you're going to have a negative exponent, right? You have to bring it up as a negative, and it gets a little bit complicated. We can do it either way. I'm going to solve it with cosine, just because the author solved it with secant, so we can do it differently and make sure we get the same answer. Okay? So I'm just going to go with cosine now. Again, but if you're looking at like any of the notes, well, I don't even, never mind. So, but remember these notes where I told you a lot of these come from? Where did they come from? Who remembers? What was the internet source that I use a lot of?
Oh,
What's the guy's name?
I don't know his name, but I know.
Not Khan Academy.
Oh, no.
I told you guys like 2 classes. There's an online site called Paul's Online Textbook for Calculus, where a guy writes a lot of these types of problems, and sometimes this is one of the ones that I use from it.
But like reading that, that's the technical. That's the difficult. Like, are you sure we would understand that version instead of this?
It doesn't matter because what? Cosine and secant are reciprocal functions. So either you can differentiate this one, or you can differentiate this one. if you happen to forget that the derivative of secant is secant tangent, or tangent squared, secant tangent, right first time, wow. So the derivative of secant is secant tangent, that might get a little messy, so maybe you want to use the cosine, because the derivative of cosine is just negative sine, that's an easy one, okay? Now, looking at the left side, again, we're not going to do this way, we could do that way, even though it's easier with this way. I'm going to show you this way just for the heck of it. Take the derivative of both sides with respect to time.
So that's D.
What does this become?
Negative
Isn't that the D?
Negative sine of,
Okay, then
what do I have to put next to it always? Very good. Remember, guys, when you take the derivative, even though it's a theta now, you still repeat it, or you take the derivative, which is negative sine, and then always write the d theta dt next to it. On the right side, what's the derivative of 50 over x?
It's zero minus x over.
You're doing a product or quotient rule, dude? Come on, stop with that. No. Move this up, make it x to the negative 1. And now it doesn't exist there. Negative 50, x to the negative 2. Again, people, when you have a quotient, if the bottom is a monomial, one term, like 4x or 12x or 20x, move it up, make it a negative exponent, then use the power rule. Bring down the negative 1, makes that negative 50. Reduce this by 1, making it a negative 2. Okay? Now, at this point in time, we have to apply what to the side of it? dx dt. Okay? All right.
We're just plugging stuff now.
Yeah, we're just going to plug in at this point, it looks like. All right.
But wasn't that D?
So, we know what theta is, right? Theta is 0.5 radians. We know d theta dt. That was given as 0.01. We know the value of x. Let's take a look. I'm trying to think of how to do this in easier way. Because they did it differently. Maybe that's why they did it with secant, because it doesn't work. Hold on. Yeah, okay.
Yeah, start
That's enough. No. I just want to show you. Look at this point, guys. We don't have a value for x. That's the problem right now. We don't know what x is.
Right.
If we did it this way, with x up top,
Right.
when you take the derivative of x, what does it become? 1. So does x take it have an effect in this problem, really? That's why the author chose this method. And he didn't write that. I'm trying to realize why it happened. It doesn't matter either way. But here, if you don't know what x is, you can't actually plug in a number there.
Right.
We're never going to know what the value of x is. Okay? We could start writing it with y's and stuff, but it'd be a lot of messier work. So at this point in time, you would plug in, but we're having an issue here, again, because we don't know what the value of x is. So let's continue and just solve it this way. So we have
Right.
secant theta equals x over 50 instead. Same exact problem, okay? We're ignoring what we just did for differentiate and do it this way. This becomes secant theta, tangent theta, d theta dt. Again, that's the derivative of secant. X over 50, the derivative is just going to be 1 over 50 dx dt. And that is a lot easier to solve. You have no x anymore. Remember, this is like saying x times 1 over 50, or the coefficient is 1x over 50 here. Okay, whatever's left is just the coefficient, 1 over 50 dx dt. Move the 50 over. Okay, and then just plug in. Theta is a half radian, right? 0.5. What was d theta dt? 001 or 01? Rad per minute?
The prom committee meeting will start momentarily in room 204.
Now, the last thing I want you guys to notice is this.
204 in just a few minutes.
When you take the secant of 0.5 radians, the units drop off. Think about it. If you took the sine of 30, what's the sine of 30 degrees? What is it? 1/2. Are there any units on that? But what happened to the degrees? Where'd they go? They drop off. Same thing. So don't try and cancel radians or multiply your radians here. Because in your calculator, when you do secant of a half a radian, or 0.5 radians here, okay, 0.5 radians, well, 0.5 radians is not going to be a number. It's not like pi over 2 or something. But whatever this turns out to be as a decimal, okay, you don't have units on it. You don't have units here. So your units will still be radians per minute. Okay, your students, your units here will still be in radians per minute. Why does that not make sense to me?
It's not a radius cube.
This bothers me because the author ignores this, but to me that doesn't make sense. What do you get for a number here? When you multiply through, you're going to get 0.3113. Now, before we put the final answer up, these units don't matter. They're no units. 50 has no units. The units here are radians per minute. The problem I'm having right now is that my units would still be radians per minute. But clearly, dx dt should not be radians per minute. What should it be? A distance per minute. X is a distance, isn't it?
Yes.
Theta was radians. So this should really be like feet per minute.
Well, the 50 feet, because
Ah, there it is. Thank you, sir. 50 feet. Okay? So there's where our feet comes in. But again, take a look even here, guys. This radian doesn't actually cancel out, which is what bothers me. He's ignoring the radians as an author. He's saying, I don't care about the radians here. But they kind of do. It should really be feet radians per minute. But the answer is feet per minute. Okay, a problem in the SAT would not have a unit confusion at all. Okay?
Keep
Thank
it
you.
SAT.
AP exam.
Yeah, you said SAT like twice.
Did I say it before? Sorry.
I'm better with that 60.
So what I want you guys to do, tonight and tomorrow night, you have 2 nights to do this.
Damn holes in it.
Write this down because you're not solving these problems. Here's what you're doing. I want you to look at numbers 1 through 4. Okay, there are 21 example problems here with written solutions, all handwritten on how to do everything. Okay, all the solutions are handwritten. Now, I want you to go through 1 through 4 and identify DREDS for every one of them. That's all I'm asking you to do. Okay? So, numbers 1 through 4, identify, and what I mean by identify is literally write it on the page. Show me where they're doing each step of the process. If they don't do a step, write. They don't do, if you don't show a diagram, write no diagram, so there's no D. They're going to show related rates. They're going to show the equation. I want you to read through the first 4. I want you to understand them as well. So please list where they are, identify, and literally read through the problems. Okay? Once we spend another class, I'll give you practice problems for yourself. Again, there's a lot here. We're going to be doing all 21 of these eventually. So keep them in your packet. They're whole bunch of staples, put them right in your monitor. Is anyone going to see anybody that's not here? Who are we missing? Kenny? Edgar? And Rosie left early, yeah. Okay, no one's going to see any of them, right? In the next 2 days?
I might see Kenny.
You see Rosalind? Do you mind just passing along? Thank you.
I'll see Kenny.
In the morning? Does anybody see Edgar in the morning? Does he come in?
I think you go straight.
Okay. All right. Well, I'll put a link to this on Facebook, this packet. So if you talk to Edgar, Christian,
Yeah.
let him know. It's recorded, so he'll see it.
But let's get wet.